So in our final section for this class, we're going to be putting together some of the ideas we've been talking about, specifically Markov chains and Monte Carlo techniques, so that MCMC methods that you've maybe heard of. So remember what we talked about at the end of the last video. We had this very important result that if we have a Markov chain with some very specific properties, it guaranteed the existence of a unique distribution, pi, and what this distribution gave us is the probability of starting off in state I, going to state j in n steps. So as we take more and more steps as n goes to infinity, the probability of starting in any state I and ending up in state j, that probability exists, and it's independent of I. Notice here, this probability just has subscript j, the probability of ending up in state j. Who cares what this state I is, where your chain was initialized? And that probability distribution specifically is unique as well. And we called this unique distribution our stationary distribution. So one more time, it tells us the probability of ending up in any particular state after we take a whole lot of steps or make a whole lot of transitions in our Markov chain. We had the same idea in the continuous case. We had this stationary distribution was guaranteed when our Markov chain met some very specific criteria. So in the next section, we're going to look at the Metropolis-Hastings Algorithm. The idea is we will construct a Markov chain using this algorithm that satisfies those very specific properties. And since it satisfies the specific properties, it gives us the existence of this unique stationary distribution. Then to combine this with our idea of Monte Carlo methods, we're going to randomly sample from this Markov chain for many, many steps, and it will give us this target distribution or stationary distribution that we're interested in sampling from. So we get samples from the distribution of interest by running a Markov chain for a long, long time, and that chain happens to have our target distribution equal to the stationary distribution of interest. So let's check it out on the next page. This first paragraph here basically sums up what I just mentioned. So the Metropolis-Hastings algorithm is a type of acceptance-rejection algorithm. And you'll see we've got some familiar terminology here. Our goal or our target distribution is to sample x from some distribution f. We're going to construct the chain using the Metropolis-Hastings algorithm in such a way that f, our target distribution, is the stationary distribution of our chain. To do this, we just need a proposal density, q of y given x. So y is our proposed random variable, and it may or may not depend on x, this value where our chain currently resides. So how to choose q? We have a few criteria, and some of these also may sound familiar. First, we need it to be easy to sample from. We should be able to draw samples from our proposal distribution. This is also familiar. The support of f, our target, needs to be contained in the support of our proposal. And then finally, we need to be able to actually write down the distribution of our proposal density. This might seem weird to you now because we've always been able to write down our distributions, but some models are so complicated maybe we can't. So we need to be able to write down the functional form of the distribution, and by that we mean the kernel. The normalizing constant is not important. We need the kernel of the distribution, or we need the distribution to be symmetric, meaning q of y given x is the same thing as q of x given y. So one of those two criteria, and you'll understand why in just a moment. So the algorithm itself looks kind of like our standard acceptance rejection algorithm. To generate values from the stationary distribution, we're first going to initialize our chain. So initialize x arbitrarily. We mentioned your probability of ending in any given state does not matter on where you started. So everybody can have different starting points. We're all going to get to the same end point, that same stationary distribution f. So initialize x arbitrarily in the space of x, and then set your time step to be 1. Next, we need to figure out where we're going next. And hence the name, acceptance or rejection. We have two options. We can propose a value and move to that new value or accept, or we can reject and remain at our current position. So next step is to generate our candidate from this distribution, our proposal distribution. Then we need to figure out, are we going to accept or reject that candidate? So xt plus 1, the next step on our Markov chain, is going to be either y, our proposed value, so this is our case where we accept, or our next step is going to be basically to stay where we are, xt. This is where we reject our proposed value. And our probability for accepting or rejecting is determined by this function rho. And rho, you'll see here, is a function of where we currently are and our proposed value. And specifically, it's the minimum of 1 and this kind of odd-looking ratio here. So I'm going to give you guys some specific cases of proposal distributions to help you get a little more of an intuitive feel for this interesting ratio we have. And before we do that, I'll just point out, of course, after we've decided where we're going to go, have we accepted or rejected? Are we staying or going to the proposed value? We'll update our time step, t is t plus 1, and we'll just continue generating more steps in our Markov chain. So some variations on this, and specifically variations on our proposal distribution, that y from q of y given x. The first variation is this idea of a Metropolis sampler. So when we say Metropolis sampler, we mean that our distribution is symmetric, our proposal distribution. So if our proposal distribution is symmetric, q of x given y is the same thing as y given x. So looking at our criteria for the probability of acceptance, this part of our fraction is basically going to cancel out, and we're left with the target evaluated at our proposed value versus the target evaluated at our current position. So a couple of cases here. If that ratio is at least 1, then rho, our probability of acceptance, is going to be 1 because we've got the minimum of 1 and something bigger than 1. So that will be 1, so that means for sure we accept the candidate. So pausing for a moment, look at this. This ratio is telling us f, our target distribution evaluated at y, over our target distribution evaluated at our current position. So in other words, if that's at least 1, that's telling me that f of y is at least f of xt. Or in other words, our proposed value is more likely under our target distribution than our current position. So it makes perfect sense that we would accept our proposed value since it's more likely than our current position. On the other hand, if f of y over f of xt is less than 1, so that's telling me my denominator is bigger, or my current position is more likely, then rho is going to be less than 1. I'm not guaranteed to accept my proposed value. I could accept it. I might consider exploring the space, stepping out into a different state. I'm going to explore it with some probability, and specifically I'm going to accept that candidate value with some probability f of y over f of xt. So if you think about this, the less and less likely my proposed value is, the smaller this ratio is, or the less likely I'm going to accept my candidate. So less likely y is for the target distribution, the less likely of acceptance, or the less likely to be accepted. Sorry, this isn't proper English here, but you guys know what I mean. So less likely y is for the target, so smaller the numerator, this whole term will be smaller, and we're less likely to go explore that state or that particular position. So that's one variation for our proposal that kind of gives you some intuition on that ratio. Let's close with a couple other variations here. So the next variation is this idea of an independent sampler. And all that means is that this ratio, or a proposed distribution, q of y given xt, does not depend on our current position at all. So you'll notice there is no xt here. It's independent of our current position. So rho looks something like this. And you'll notice rho will be closer to 1 more frequently the closer f and q are. The numerator and denominator will be much closer to each other the closer f and q, my target and my proposal, are. So I'll just make the comment here. This is going to be more efficient when f and q are, and I'll put in quotes here, closer. Okay. All right, and then the final variation I want to mention is this idea of a random walk sampler. And by random walk, we mean we have this definition for defining our new position. So here, I've got it written out as a formula, also in plain English. So y is our proposed value. We're going to generate our proposed value by saying, let's check out where we currently are and add to it some random error. And specifically, this random error needs to be symmetric, so think like from a normal distribution. From your current position, you're going to go up or down some random amount, some random error. And for this one, convergence is highly sensitive to your choice here for this random error. Are you going to go out and take huge leaps on either side of where you are, or are you going to take baby steps on either side of where you are? And in a couple of videos, when we go over example 2, we'll see exactly what we mean by this. So one last observation here. Notice that our normalizing constants are going to cancel out in all of these cases, which is why we made that criteria that we need to be able to write down an expression for the kernel of the distribution for our proposal. But check out this ratio here. The normalizing constants would cancel out, so no need to worry about being able to actually find those or calculate those normalizing constants. All right, so that's the idea of the Metropolis-Hastings algorithm. In the next section, we're going to check out an example.